Alright, hello College Algebra. Here we are again in Chapter 1, in Section 3. We're going to be talking about complex numbers. And the reason we're talking about complex numbers now is because in the next section we'll be doing quadratic equations, and some of those solutions will end up being complex or imaginary, or complex imaginary solutions. So let's get started. So there is no real number solution to the equation x squared equals negative 1. And since there is no real number, when we square both sides of that equation, what happens is the square root of negative 1 is just known as the imaginary number, or I is what we'll call it. And this down here at the bottom, let me highlight it right here, we're going to say x squared is equal to negative 1. Okay. Now, if a and b are real numbers, then any number of the form a plus bi is a complex number. And in the complex number, a plus bi, a is the real part and b is the imaginary part, or bi is the imaginary part. So when we do some examples, you'll hear me say, let's add together the real part, add together the imaginary part. And those two things are, the imaginary parts are like terms in solutions, and also the real part are like terms whenever we go to add them together or subtract them. So two complex numbers, a plus bi and c plus di, are equal provided that their real parts are equal. So like you see down here, a plus bi is equal to c plus di if and only if a is equal to c and b is equal to d. That's just a basic concept that we're going to be following. For complex numbers, a plus bi, if b is 0, then you have a plus bi equals a. Therefore, it's no longer an imaginary number or a complex number, it's a real solution. So if a is equal to 0 in our complex solution, what that is known as is a pure imaginary number, because you're just going to be left with bi, the imaginary part. So this is a pure imaginary number. Let's see, look down here. A complex number written in the form of a plus bi or a plus ib is in standard form. So whenever we're asked to find a solution in standard form or write a value in standard form, these are the two forms that they will be in, a plus bi or a plus ib. Here's the set of real numbers and complex numbers. As you can see, right here are the set of all real numbers, and a completely different set is over here. These are the types of numbers we are dealing with in this section here. So let's move on. Like we did, like I said before already, here's non-real complex numbers. It's in the form of a plus bi. And pure imaginary numbers are just going to be some number times I, or just I itself sometimes. The expression square root of negative a, if a is greater than 0, then we have the square root of negative a is equal to I, we're just going to change it to I square root of a. Okay, so that's going to go along with our first example that we end up doing, like these here. Before you take the square root of anything, if there is a negative inside that radical, the first step we're going to do is just take the negative away and put an I in front of the square root. So let's do that with this first one. So we're asked to write as a product of a real number and I. Take the I out, and that becomes square root of 81. And we should know square root of 81 is 9. So the solution to this problem is 9i. And we're done. This next one, part B here, we're going to do the same thing. Take I out, or the negative out of the square root. And we end up with I equals square root of 55. Now, the square root of 55, the only factors that 55 actually breaks down into are 5 and 11. Neither of these you can take the square root of. So we're actually just going to leave this in this answer as our answer right here. That was our solution for the other one. Now let's move on to part C here. Again, take the I out, and we're left with I square root of 98. And this one actually we can break down. 98 breaks down into 49 and 2. You can take the square root of 49. I'm going to cover it in steps here. Okay. So taking the square root of 49, that we can take that out of the radical, but to do that you have to take the square root of it. So the square root of 49 is 7. Bring it outside the radical, so we now have 7i times the square root of 2. And you cannot take the square root of 2 without it being a decimal number. So we're just going to leave it as is, like this. This is our solution. Okay, let's move on. Here's some more operations on complex numbers. Products or quotients with negative radicands are simplified by first rewriting the square root of negative a as I square root of a for a positive number a. Okay, so let's move on to the next slide and I'll explain it further. Here's what that previous slide was referring to, and what I want y'all to watch out for is we should know this particular rule right here. The square root of c times the square root of d, or the square root of some number times the square root of another number, is equal to the square root of those two numbers multiplied together. But this is only valid when c and d are not both negative. Okay, so here this example, there's two ways of solving it, but only one way is correct. See how this one, we go from square root of negative 4 times square root of negative 9 to 2i times 3i. That is the correct way to do this. We are first going to take I out of the radical and then take the square root of our number. And in this case, we end up with 2i times 3i. And then we multiply those together to get 6i squared. I squared, as you've seen in a previous slide, is negative 1. So the correct answer for this is negative 6. If you were to come back up here to this rule here, if you were to follow that rule, like I said, you should not follow that rule whenever you have two negative values inside square roots. First, take the I out and then solve for your answer. That would be the correct version. this is not correct. Okay, so please take the I out of the square root first. So let's put that rule to use. So here we have, again, we have negatives in both of our radicals. Take those out first. So we end up with I times the square root of 21 times I times the square root of 21. This ends up giving us I squared times the square root of 21 squared. Sorry, forgot my squared. There. And I squared, like I said before, that is -1. The square root of a number squared is just that number, so say times 21. And we get our solution is -21. Let's do this again. For this problem, there's several more steps to this one. So follow along. Take the imaginary part out. Take the I out of the square root. I square root of 5 times I square root of 30. Okay, so again, now that both numbers are positive inside the square root, we can use that rule that we previously covered in the previous slide. Let's do that. So I times I, that's I squared, and square root of 5 times the square root of 30, that gives us the square root of 150. Now, I'm going to go ahead and say, well, I squared is -1. And we're going to multiply that to what's left over, the square root of 150. But let's break down 150 into two factors, which one factor we can take the square root of. The one thing that I can think of is 25 and 6, the two factors that I think of. So, the number 25, you can take the square root of that. So let's do that. We end up with -5, because the square root of 25 is 5. Then you multiply it to that -1 that we already have. And then what's left over in the radical is our 6. So there's our solution, -5 square root of 6. Have a couple more here. So this one we are dividing imaginary numbers or complex numbers here. The first thing in division, first thing you need to know about division is what we're going to do is we are going to take the radical or the imaginary number out of the denominator. That's the whole point of simplifying fractions that are complex or imaginary, is get that complex number out of the denominator. And the way we're going to do that is by multiplying both numerator and denominator by what is in our denominator. That's the usual steps. But this first one is something that I see, just like multiplication. We need to take that I, the imaginary number, out of the radical first. Get rid of that negative. So we have I square root of 42, I square root of 3. Now our i's end up canceling each other out. So we end up with square root of 42 over the square root of 3. And if you remember the division rule, this is the same thing, the square root of 42 over the square root of 3 is the same thing as the square root of 42 divided by 3. And doing that division, 42 divided by 3 gives us 14. So our answer is the square root of 14. And there aren't any factors of 14 that you can actually take the square root of and the number come out evenly. So this is our solution. Our next one, D here, just like the previous ones, we always took the negative out of the radical first. There's no negative in the denominator, so just rewrite that as is. And then the next step would be, well, this time our i's don't cancel out. We keep our imaginary number. And we can put together, just like we did in the step above, the square root of 63 over the square root of 21. We can put those together in the same radical. And that ends up simplifying to I times the square root of 3. And that is our solution. Okay, here in this example, we are asked to write our number here in standard form. So A plus BI or A plus IB. And what we're going to do is first, I am going to take that negative out of the radical that you see here. And then do my steps from there. So 15 minus I square root 75 all over 5. Now I'm going to break apart what's inside the radical, the 75, into two factors. And two factors I know in which one number can be taken the square root, well, you can take the square root of, is 25 and 3. So now, taking the square root of 25 in our next step, we end up with 15 minus square root of 25 is 5. So you got 5i on the outside, and on the inside of the radical, a 3. Still all divided by 5. Now, my next step here is, in this numerator, both terms, 15 and 5i square root of 3, those both have the factor of 5. So let's factor out of 5. And we factor out of 5 from this first term, 15, we're left with a 3. And we factor out of 5 from the second term, 5i square root of 3, we end up with I square root of 3. And now, hopefully you can see what our last step is going to be. We're going to simply cancel these 5's out. And our final answer, or solution here, is going to be 3 minus I square root of 3. And there you go. Finally got our answer. Alright, addition and subtraction of complex numbers. Like I stated earlier, what we're going to be doing for these, when we add together complex numbers, all we're doing, or even subtracting complex numbers, what we're going to be doing is adding or subtracting the real parts, and then adding or subtracting the imaginary parts together. And that's all this is stating right here. See, A plus C right here, those are the real parts we put together. And BI and DI, those are the imaginary parts that we put together. And same goes with subtraction, except it's going to be A minus C and BI minus DI. Okay? So let's put those things to use. So we're asked to find each sum or difference of these two complex numbers. And we have a real part, we have an imaginary part. Put the two parts together. So we have 4 plus a negative 5, or 4 minus 5, is going to be our real part. And then our imaginary part is going to be our negative 5i plus 8i. So next step is add them together or subtract them. So 4 minus 5 gives us negative 1. And then the negative 5i plus 8, that gives us plus 3i. Okay? And there we have it. We added two complex numbers. Now the next one, we are subtracting. There's two ways we can go about doing this. I'm going to show you one way, is by distributing that negative throughout this second term first beforehand, okay? And I'm going to take away the parentheses on this in here first for getting started. So we get negative 10 plus 7i. And then we have a negative 5 plus 3i. Just like before, add or subtract the real parts, add and subtract the imaginary parts. So we have a negative 10 minus 5, that gives us a negative 15. So that's these two put together. And then these two put together, we end up with 7i plus 3i. That gives us plus 10i. And there we go. Our solution. Now we're going to be multiplying complex numbers. And just like you've learned in algebra before, the foiling method, which means first, outer, inner, last, we're going to be multiplying the first two terms together, the outer two terms together, the inner, and the last. Okay? That's the way we're going to be multiplying complex numbers. And that's what all these steps are taking right here. Okay? And I don't know why I put that slide in there, but here we go. It says find each product. Okay? Let's foil these things together. We have first 5 times 2 gives us 10. I'm going to write it out here. 10. Outer, so 5 times a negative 7i, so it gives us negative 35i. Inner, a 3i times 2, so plus 6i. And last, 3i times a negative 7i. That's going to give us a negative 21i squared. Just like if you're multiplying x times x, it ends up being x squared. Same goes with imaginary numbers. I times I is I squared. But we know I squared is also -1. So let's write this down. Let's combine terms. Our imaginaries, combine those, and our real numbers, we're going to combine those. -35i plus a 6i, that's going to give us, let's see, -29i. And like I stated before, this I squared is going to be a -1. So we're going to multiply our -21 to -1 to end up getting a positive number. So this ends up being positive 21. Which ends up being a real number. So we add that real number to our real number here at the beginning, 10, to end up with 31, and then minus our imaginary part, 29i. And there's our solution. Okay, on this next one, what we have is exactly what we did in part A. You can do it just like that, except this, if you want to FOIL it, make sure you rewrite it just like this. Okay, multiplying this what's inside our parentheses together twice. I kind of simplify it though. Here's what I'm going to do. Instead of foiling that all out, what I do is I say, this first term, let's square it, okay? And now our middle term is going to end up being, it's right here, 4 times -5i times 2. So 2 times 4 times -5i is our middle term. And then our last term is -5i squared. So plus -5i squared. Now simplify this. When we simplify this, what we end up with, what we end up with is, 4 squared, that's 16. And then all of this, 2 times 4 times -5i, that ends up giving us 40i. And then this over here, -5i squared, that gives us 25i squared. Because -5 times a -5 is a positive 25. But that I squared is -1, so it's going to change it back to a negative anyway. So we end up with 16 plus 40i minus 25. And then the last step is to combine together our 16 and our -25. And that ends up being -9 minus 40i. And there's our solution. Okay, almost done. Last thing we're going to look at is a property of complex conjugates. Now, conjugates are the in here. Okay, look inside this set of parentheses right here. In this set of parentheses, we have a plus bi. In this set of parentheses, we have a minus bi. Nothing changed about our real numbers, a and b. The only thing that changed is the sign that's in between them. Those are conjugates. Okay? Just change the sign in between our conjugates. And whenever we multiply two complex conjugates together, the only thing we have to end up doing is multiplying the first two terms together and the last two terms together. And this is what we're going to end up with. A squared plus our b squared. And we're done. Okay? So we're going to end up with a real solution for complex conjugates. Here we go. Find the product. This is a complex conjugate because nothing changes about these numbers here except for the signs in between them. So we're going to square 9 and then we're going to square 8 and we're done. Almost done anyway. So square, or 9 squared plus our 8 squared, which gives us 81 plus 64. And we end up with our final solution being 145. That's our answer. Let me know if you want to, if I can show you how to do this on your TI-83s or 84s. You can change your screen to display imaginary results. Let me know if you want to do that. Okay, last thing here. So we're asked to write this value here that we're given in standard form, a plus bi. How we're going to do that is similar to how we did this before, writing a fraction, a complex fraction in standard form. So let's get started. How I'm going to show you how to do this is we're going to multiply. We're going to apply the theorem about our conjugates. What we're going to be doing is getting the imaginary number out of the denominator. And if we multiply both numerator and denominator by the conjugate of our 3 plus I, we'll end up with a real number inside our denominator. Okay, so that is what we're going to be doing here. Multiply both numerator and denominator by the conjugate of that denominator. And after you write this step out, what we're going to do with the numerator is multiply these out, and then again denominator will multiply these out. Okay, so to multiply the numerators together, FOIL it. So first we get 15 outer, inner, and last. And that is going to be divided by our denominators multiplied together. So 9 plus, well, the number in front of I here in this case is 1, so 1 squared. which is 1. Okay, so let's simplify this a little bit further. We can put together our imaginary numbers, the negative 5i and the negative 15i. To get negative 20i. And then 5i squared, we can rewrite that as negative 5 because our I squared is negative 1. 9 plus 1 gives us 10. We can go a couple more steps in simplifying this. Let's do that. So now put the real parts together, the 15 and the negative 5. That's going to give us 10 minus 20i over 10. And a common factor between all three of these numbers is this 10 here, and this 20, and this 10 right here is 10. So let's divide everything by 10, and that's our last step. We get 1 minus 2i. And that's our final solution. That's it's our number in lowest terms and in standard form. And there we have it. That's the last thing I have for you on complex numbers. So, see you in the next section.